So we're going to look at two applications where the law of sines can help us answer the questions. So with this first case, we have two ships, A and B, that are 60 miles apart. Ship A is directly north of ship B. So what that would look like is, let's say I draw, A and B, and they are ship A is directly north. So that means it would be going up that way is north. So this would be ship A is directly north of ship B. And then we're told that they're 60 miles apart. So we also know this distance right here is 60 miles. Oh, there's part of our picture. They both receive a distress signal from a third ship at the same time. Ship A receives the signal from a direction 35 degrees south of east. So what that means is if I go to A and I visualize my compass, something like this. So here's north, east, south, west. And they just said that the signal was 35 degrees south of east. So here's east, and we're going 35 degrees south of that. So it's kind of like a negative 35 degrees right there. So I can imagine is kind of sending out to this distress signal. Maybe I could continue a line that looks something like that, where right here is a measurement of 35 degrees. And then without knowing where this third ship is, I'm just going to continue that line on. I'll go kind of dramatic with it of forever like that. So with that, the distress signal for that third ship is somewhere along this line that's 35 degrees south of east. Ship B receives that same signal, a direction 50 degrees north of east. So what that would look like here is if I visualize my kind of compass, I have north, east, south, west. So we're going 50 degrees north of east. So we're going in this direction. So 50 degrees maybe looks something like that-ish, where this measurement right here is 50 degrees. And then what I'm going to do is just continue that line on as straight as I can. So where those two intersect, that's where the third ship is, which I'll call ship C. And then I'm just going to delete all this other stuff. All right, so what we want to know is how far is the third ship from ship A? So what I want to find is this distance right here. Now, we made a triangle here. So we have this triangle, and all we have right now is actually one side length and nothing else technically inside the triangle. However, we have these relationships where we can find some angles here. So like if I go down here to ship B, this makes a 90-degree angle right here. So if this is 50 degrees, then this has to be 40 degrees right there. So those have to add up to 90 degrees. So that gives me an angle inside. Same thing is true up here at the 35 degrees. Those need to add up to 90. So if you take 90 minus 35, that'll give us the 55 degrees that's inside right there. So with that, we have an angle side angle. If we needed to, we could find that 85 degrees right there, which we actually will. So my thinking here is, here's our unknown. We know the opposite angle. That's a good pairing to have for law of sines. We have 55 degrees with no information and also a side that we're not interested in finding. So that 55 degrees I'm probably not going to use. So this is where I need that angle measurement here so that it can work together with 60. So what I would do is 180 minus 40 minus 55, and that'll give us 85 degrees right there. So now I have, using law of sines, I have a nice pair to work with. So Sine of 85 degrees over 60 miles is equal to, and then working with x, I'm going to work with that 40 degrees. So I'm going to have sine of 40 degrees over the unknown x. Now we're going to solve for x. So we can cross multiply. And then divide by that sine of 85 degrees. And then we would just plug it into a calculator. So from the calculator, that should give 38.71, and that's in miles. So big part of these is drawing the picture as best you can. Then with those, when you're using these directions, there are these properties of 90 degrees coming through that can help us out to fill in some of the blanks. All right, let's look at another one. Here we have a balloon is sighted from 2 points on level ground. One point had an angle of elevation of 18 degrees, and another point angle of elevation of 12 degrees, and those 2 points are going to be 80.4 meters apart. In this first one, they're going to be on the same side of the balloon. So it's kind of like they're standing in a field, I mean, they're far apart, 80.4 meters, but kind of going towards the same direction of looking at this balloon. So let's go ahead and draw a picture here of what that would look like. So here's our field or whatever we're standing in. Out there somewhere is a balloon. And there's going to be 2 viewpoints. Let's go ahead and draw these. Let's say one of them is there and one of them is there. Now to know which one's A and B, so B has an angle of elevation of 12 degrees and then A has one that's larger. In comparing these angle measurements, as you get closer and closer to the object, that angle is going to grow and grow until you get to 90 degrees. So larger angles will be closer to the balloon. So that means this should be the 18 degrees, which would line up with point A, and this should be the 12 degrees, which would line up with point B. All right, and what we're interested in is the height of the balloon, which would form with the ground at a 90-degree angle. So we want to find that height. Another piece of information we're given is how far apart A and B are. So that distance between A and B is 80.4 meters. Sorry. All right, so we have these pieces of information and we want to find what the height is. So we have a few triangles that we're working with here. We have this kind of right triangles that we're working with. We have this oblique triangle right here. And what we can do is with that oblique triangle, because with H, I'm going to be pretty stuck because I don't have any other side lengths to the triangle. I don't have a side length there. I don't have a side length overall for this larger triangle. Same thing, not even for that triangle. So with my right triangle, I'm really getting stuck because I don't know any of the side lengths. But what I could do is focus on this oblique triangle here, and I have this angle measurement. I have this side length. I can do some work to find the other angle measurements. So let's focus on finding this side length here. So let's see if that can come about once I fill in some more angle measurements, because I have one side already of that triangle, so that's what's making me focus on this one. And if it helps, you can always draw this off to the side too. Like if it helps to draw your triangle out there so that you just see 80.4 and 12 degrees and then filling in the rest, that absolutely works. Now, we can fill in this angle measurement here with that 18 degrees. That should be a total of 180 degrees. So 180 minus 18 is going to be 162 degrees. And then we can find our third angle. So 180 minus 162 minus 12, and that should be 6 degrees. So in terms of my triangle, I could go back here and try to write this in. We have all three angle measurements, which is helpful. We have one side length. So what we're seeing here is that you could think of this as angle, angle, side, angle. I think that would be about it. But we should be able to use law of sines here because we have an angle paired with its opposite side length, and we have an unknown side length with its angle measurement. So what that would look like is sine of 6 degrees to that 80.4 would be equal to, and then working with x, we would be looking at that 162 degrees over x. And then we would just solve for x. So cross multiply, then divide. So in the calculator, we put 80.4 times sine of 162 degrees over sine of 6 degrees. And that's going to give x of 237.69. So what we just found there is this side length out here. So now if I look at my right triangle, I have more information. So if I grab this kind of big right triangle with that balloon, where we have, this is our height, out here was our 12 degrees, and then we just found this side length of 237.69. Well, let's see, I have an angle. We're looking for our opposite side length. We have the hypotenuse. This is a great recipe for just using our standard trig function, sine. So from SOHCAHTOA, sine of that 12 degrees should be equal to opposite over hypotenuse. And we can do this because it is a right triangle by finding that height off of the ground for the balloon. So in the calculator, we're going to multiply 237.69 times sine of 12. And that's going to give a height of 49.42 meters. Will be our final answer. So with that, putting the picture together, and then you can just start filling in pieces until it works. You'll have information to probably fill in more than you need to, but however many steps you need to get to that final answer is fine. All right, this last example here. So we're going to do the same thing, but now A and B are going to be on opposite sides of the balloon. So what that's going to look like is the balloon will be in between these two people that are looking at it. So here's going to be our balloon. And then let's go ahead and call this A and this B. And we'll say that's 18 degrees, even though it looks like a lot more. I didn't draw that really to scale. Same thing over here with 12 degrees. And again, we want to find the height. And this time we're being told the distance between A and B, which spans all of that, is 80.4. All right, so in terms of right triangles, again, we're going to be stuck. Like this right triangle, all we have is that angle and nothing else. Same thing over here. So what I want to do is actually look at the big triangle, which I could draw off to the side here. The big triangle where this is 18 degrees, this is 12 degrees, and this is 80.4. Because then I can see my angle side angle. So I'm going to need that opposite angle up there. So 180 minus 18 minus 12, that should be 150. So we have 150 degrees up there, and that gives me a nice pairing to work with. And then I just need to choose a side. Either one, it's all going to balance out in the end, so it doesn't matter which route you go. Let's go ahead and solve for this side. But there's nothing in the wording of the problem that's making me choose that. You could do it that this is x and solve for that. That's completely fine too. I'm just going to call that my unknown over there. So what we'll have is sine of 150 degrees over 80.4 is equal to, and then I'm going to use x in the 18 degrees. So sine of 18 degrees over x. And then solving and plugging into the calculator, just to skip ahead a little bit for the sake of time, should be a 49.69. So we just found this side length right here. Meters and meters. All right, now with that, let's take a look at this right triangle where we just got an extra side length. So we don't know what the height is. We know this is 12 degrees down here, and we have this 49.69. So for our angle measurement, we're looking for the opposite side length. We have the hypotenuse, so that means we can look at, with a right triangle, sine of 12 degrees is equal to opposite over hypotenuse. And then we just solve for h, and that should give 10.33 meters for our final answer. So there's some applications. It really comes down to getting the drawing correct, and then with that, just kind of playing with the triangles until you get the side length or angle measurement that you're looking for.